master. Yeah. Thank you.
Distinguished speaker of Earth Day, Dr. Krishnan, my dear colleagues from CSIR NGRI, members of CSIR NGRI Research Council, former directors, friends. Very good morning and greetings to all of you on International Earth Day. I understand that first International Earth Day was celebrated in the year 1990 with participation of more than 200 million people from 141 countries after almost 2 decades of movement about keeping Earth environment clean. In fact, the movement started in 1970. Presently, more than 193 countries celebrate the International Earth Day on April 22nd. Various events are organized to create awareness and inspire people to take Mother Earth and its natural environment having significant implications for longevity of the generation. This day serves as a conscious reminder of how fragile our planet is and how important it is to protect our planet Earth. The recent pandemic was a befitting situation. We realized that non-interference or anthropogenic activities which are derived by human helps nature to regenerate to great extent. At the CSIR-National Geophysical Research Institute, we are back to our usual page of the Earth Day celebrations with organizing of various events, including the Earth Day lecture by an eminent scientist. And this is an integral part of the events every year. We are glad to virtually welcome Dr. R. Krishnan, Director of Indian Institute of Tropical Meteorology, Pune, for this year's Earth Day lecture at CSIR. Dr. Krishnan is eminently known climate scientist who have recently contributed to the sixth assessment report of IPCC working group 1 as lead author. Very distinct honor for an Indian researcher. His research interests are broadly in the area of climate modeling and analysis, which consist of global climate change and variability, climate dynamics pertaining to the Indian region, global and monsoon hydrological cycle. And as you all are very much aware, present era when large We are very fortunate that Dr. Krishnan chose to speak similar topic. Dr. Krishnan is graduate from MIT and served at Tropical Biology and Science Division of the Director of the same prestigious climate. Name a few MOES National Award in the field of this is this brief introduction. I feel privileged and honored present before you the Earth Day speaker, Dr. Krishna. Krishna, again, thank you for inviting us.
Yeah. Thank you, Dr. Virendra Tiwari, for your very kind and nice introduction. And good morning to you, sir, and also Dr. Purnachandra Rao, former colleague in MOES, and all the participants from NGRI, all the scientists and staff. Good morning to all of you, and wish you all a wonderful Earth Day, International Earth Day. Director was speaking. Let us see if everything goes well. Yeah, so let me share my slides. So is it visible now? Hello?
Yeah, we can have it in full screen mode.
Yeah, it is in full screen only.
Not yet.
Oh, is it? Wait a minute. Is it okay now?
We can see, but it appears that's not in projection mode.
Oh,
so
okay.
Probably you may have to share your desktop and then open.
Okay.
Yeah, put F5 button. F5 button.
Stop. I'll stop sharing. I have to share my desktop, is it? Is it okay now?
Not in projection mode. Can you just F5?
Sorry. Should I give the control to?
Yeah, that's fine. We can do it from here.
Yeah, that will be good. Okay. Yeah, I'll allow. Is it okay now? Hello?
Just a moment. Yeah, we're just setting.
We are trying to just. Can you accept the request?
Okay.
Sir, excuse me.
Yeah, yes, please.
Sir,
Yeah.
after 110%, you can see small cup-like icon.
No, I didn't hear. Can you repeat?
After
Please?
110%.
Yeah, some of it is getting cut. Maybe 110 is little.
After that cup-like icon, press.
After the icon, can you move your mouse there?
Sir, can you unshare the screen, sir?
Okay.
Sir, while sharing, please click the first icon, sir. Once click the share button, you will see the first icon. This entire screen or desktop you will see, sir.
Okay, desktop. Yeah, okay. So I'll click on the desktop.
Yes, sir. Now we can see, sir.
Okay, great. Okay.
Change the slide, sir.
So the first slide, let me.
Yes, sir. We are seeing.
Yeah, is it now okay?
It's
Yes.
perfect, sir. Perfect.
Yeah. Thank you. Thanks a lot, Dr. Tiwari and colleagues from Menses. Thank you for this kind invitation. And this is a great privilege and honor for me to give this talk on monsoon hydrological cycle response to global climate change. And these are some of the key messages from the IPCC CSIR-6. So this is the summary of policymakers of the Working Group 1 report. Was released last August 2021, and then the full report will be coming out actually very soon, and of the Working Group 1 report. The Working Group report has 12 chapters. The first chapter is the framing, context and methods. Chapter 2, the changing state of the climate system. Chapter 3 on the attribution, that is the human influence on the climate system. Chapter 4 on future global climate scenario-based projections, near-term information. This is global. These chapter 2, 3 and 4. And chapter 5 to 8. 5 is on global carbon and other biogeochemical cycles and feedbacks. Chapter 6 on short-lived climate forces. Chapter 7 on the Earth's energy budget, climate feedbacks and climate sensitivity. Chapter 8 on water cycle changes, in which I was one of the coordinating lead authors. And chapter 9 on the ocean, cryosphere and sea level change. So chapter 5 through 9, they come under process studies. These are process-oriented chapters. And chapter 10, 11 and 12, they are more of regional, linking global to regional climate change, weather and climate extreme events in a changing climate. And chapter 12 on climate change information for regional impact and risk assessment. So this is the overall structure of the Working Group 1 report. And basically the water cycle changes which I will be presented is from a process-oriented perspective. That's what I want to convey. And so this is the one of the key assessment is the attribution, the human influence on the climate system is both at global and regional scales has come out very clearly from the in the AR6 assessment. So this is a very powerful statement saying that human influence has warmed the climate at a rate that is unprecedented in at least the last 2000 years. And when we look at the global mean temperature, which has increased more than, it's close to 2021, it was something close to 1.2 degrees above the pre-industrial mean temperature. And this is mainly this rise in the temperature which we are seeing since the 1850 is mainly due to the human influence, and this warming is unprecedented in the last more than 2000 years. And when we look at the multi-century period, multi-century record, this has been the warmest multi-century for in the more than 100,000 years. This is based on paleoclimate data, model simulations, observations. So this is based on multiple lines of evidence. So this statement is coming out, and the change in the global mean temperature, the annual averages as observed and simulated using these are based on the CMIP-6 models, in which IATM Earth System model also participated. So this is for the first time an Earth System model from India has participated. And this clearly shows that human and natural variations both have contributed to these increasing global mean temperatures. So this is the range of models. More than 50 models all over the world participated in the CMIP-6 process, which later on fed into the IPCC assessment, including the IATM Earth System model. So this warming, especially very pronounced increase in the global mean temperature since the mid 20th century, is largely attributable to the human influence. If we had only natural forcings like the solar radiance changes or the volcanic eruptions, they cannot explain this increasing trend. We do see some episodes of volcanoes. There are cooling episodes. This is the Pinatubo eruption in 1991. And so natural forcing can account for some of these episodic cooling events. And then you see the El Chichon in 1983, but this overall warming trend in the temperature increase that we are seeing can be attributed only if you account for the human influence, mainly the anthropogenic emissions of the greenhouse gases like carbon dioxide and methane and others. And the observed warming, as I said, is driven by emissions from human activities, which with greenhouse gas warming, that is the main contributor, and partly masked by aerosol cooling. So mainly in the northern hemisphere, these anthropogenic aerosol emissions, they have since this 60s, anthropogenic emissions of aerosols, they have contributed to cooling because they are basically cutting down the solar radiation, incoming solar radiation, and so they have kind of masked the global warming to some extent. And so basically what the models show, the CMIP-6 models show, is the observed warming 2010 to 2019 is about 1.1 degrees compared to the 1850 to 1900 period. So what the model-based attribution suggests is if we had only greenhouse gases, well-mixed greenhouse gases, the warming would have been 1.5 degree. But the moment, so basically the aerosols have kind of cooled by about 0.4 degrees, mainly the sulfur dioxide emissions and also partly other organic carbon, and also land use changes to a smaller extent. So these two main drivers, one is the greenhouse gas warming and the aerosols. This is what has affected the radiative imbalance mostly by and large. And this is particularly so we have to recognize that there are different drivers, and this is especially important when we are talking about hydrological cycle and the monsoons. This I will be coming later on. And it also says that the warming over land, the simulated and observed changes compared to 1995 to 2014 average in key large-scale indicators of climate change across the climate system for continents, that is the surface air temperature over land, and ocean basins and globally up to 2014 is shown here. So what we find is the increased warming, the black line is the observed warming for near surface temperature over land, which has during the historical period. This we can attribute it only when we have the human influence. That is from the models, the brown line which is shown here. Just with the natural forcings we cannot. That is shown by the green line. And also this is the first panel is the land temperature, and the other next panel is the global surface air temperature. You see a similar attribution. But the warming over the land area is much more pronounced compared to the warming over the oceans. But oceans have also absorbed a significant amount of heat, this I will be showing in my next slide. The increase in the ocean heat content is also attributable largely to the human influence, and this warming we see over on different continents, the continents of North America, Central and South America, Australasia, Asia, Europe and North Africa. Antarctica is a little bit tricky because in addition to the warming, there are strong decadal variations which are associated with natural variations in the system, and there are some limitations with the Antarctica and warming, and this has implications for the changes in the Antarctic sea ice. And but most of the continents, the warming which we are able to see, which we are seeing observed warming is attributed to the anthropogenic activities, and more pronounced in the Arctic. The Arctic warming has been warming at a very rapid rate, and this is one of the big concerns. And with regard to the precipitation changes, the observed precipitation global is shown by the black line. We see an increase in the precipitation after the 80s, and the models are also showing an increase with the increase both when you have the human influence, that is the carbon dioxide, greenhouse gases. So that shows the increase in the global precipitation, although the magnitude is underestimated in the models, and also the variability, the range of variability that you see in observations are underestimated in the models, but the overall warming trend can be seen even in the model projections. And when we look at the extratropical, mid-latitude and extratropical precipitation, a clear increase in the precipitation we can see from the 80s, and the models are very clearly capturing this signal. So the attribution of the mid-latitude precipitation increase due to the influence of activities is standing out very clearly. And likewise with the warming in the high latitudes and the mid-latitudes and the polar latitudes, the sea ice has declined, especially in the Arctic. And this decline in the sea ice is attributable to, again, the human influence. Antarctica is a little bit tricky, as I said, the variations, because the variations in the temperatures, due to the decadal timescale variability, there are differences in the model projections and the observations. And so much of the warming when we look at the emission energy inventory change, about 91% of the observed energy increase for the period 1971 to 2018. So during this period, much of the energy has been taken by the oceans. It has gone into the ocean, and we can see the increase in the ocean heat content trends when we look from 1971 to 2014. So in the depths of 0 to 700 meters, from the surface up to 700 meters depth ocean, we can see many areas in the warming, especially even in the Indian Ocean. So Indian Ocean has been particularly warming at a very fast rate. And we also see in the Pacific and the Atlantic Oceans, also the Southern Oceans. So this is in the surface to 700 meter depth. And when we go to deeper layers, subsurface from 0 to 2000 meters, there we also see the effect of some areas. We see the cooling. This is mostly associated with circulation changes in the deep ocean circulation. But in the Indian Ocean, a pronounced warming can be seen North Indian Ocean, and in other parts, for example, in the Northwest Pacific and also in the Southern Ocean. So these are based on the observed trends in the ocean heat content, and out of when we do this global energy inventory, we can see the warming is happening in the ocean subsurface, 0 to 700 meters, 700 to 2000 meters, and also in the deeper layers below 2000 meters at deeper depths. And also the ice, the cryosphere component of the Earth system has warmed. The land surface has warmed and atmosphere has warmed. So the energy has been taken up by the entire Earth, atmosphere, ocean, biosphere, and the cryosphere system because of the anthropogenic activities. The addition of excessive heat is being absorbed by all these components. And one more clear signal is the changes in the sea level budget. So there can be increase in the sea level due to thermal expansion of the ocean. We call it as the thermospheric sea level height changes. And there could also be changes due to mass, addition of mass, for example, melting of the glaciers or the ice sheet, and also changes in the land ocean storage. And so when we have all these components contributing to the sea level, so this is the observed global mean sea level, what is shown by the dashed line. And this is more or less explained by the different contributions coming from the thermal expansion from the oceans, as well as the mass addition from the glaciers and the ice sheets in Antarctica and Greenland, and also the land ocean storage. So they are mostly able to account for much of this increased changes that we are seeing. And this is from the CMIP-6 models. What we are seeing is the simulated and observed global mean sea level change only due to thermal expansion, that is the thermospheric sea level change in millimeters. This is shown from 1850 to till 2014, and we can see much of the increase that we are seeing in the sea level, rise in the sea level, is attributable to the human influence due to the thermal expansion. And so the human attribution element is very clearly coming out in the AR6. And what about the future projections? So for the AR6 we use the philosophy is based on the shared socio-economic pathways. We call them as SSPs. There were five different scenarios. The SSP1 is a kind of a very sustainable scenario in the future, and SSP5 is a very high emission scenario. It's a highly fossil fuel dependent scenario. And the SSP2 is kind of a middle of the road pathway, and SSP3 is a scenario where there can be regional rivalries. So the emission is determined by the regional rivalries for economic growth and so on. And SSP4 is more of inequality. So different socio-economic narratives were used in the IPCC AR6 assessment, and the SSP1 is a more of a sustainable type of approach. And what we find is, for these, based on these different scenarios, projections were made using the CMIP-6 models. And so this is just what is shown in this diagram is a socio-economic challenges for mitigation, that is on the y-axis. So on the x-axis, we have the socio-economic challenges for adaptation. So clearly the SSP1 is a kind of a low challenges, and it's a highly sustainable pathway. It's taking the green road. And when we take the SSP5 is a highly fossil fuel development pathway, taking the highway. And so we have major mitigation challenges to dominate here. And the SSP4 is associated with more of inequality, although we don't have a SSP4 in the future projections in the CMIP, but this is one of these SSP pathways. And the SSP2, it is a kind of intermediate challenges. It's a middle of the road, and which is something that we are right now following. Right now, the changes that we are following is similar to the SSP2, SSP245, and SSP3 is regional rivalry. So what we find is these are the carbon dioxide concentrations in parts per million according to the different scenarios. And we see the SSP245 is already, even though the middle of the road, doubling the carbon dioxide concentration will be almost double compared to the pre-industrial time by the end of the 21st century. And these are very high emission scenarios. The SSP370 and the 585 scenarios highly unsustainable. The 119 and the 126 are kind of low emission scenarios. And so this is just to give an idea. And now let us look at the projections, temperature global mean projections from the IPCC AR6. So what is the main assessment is the global surface temperature will continue to rise until at least the mid-century under all the emission scenarios considered. Global warming of 1.5 degree and 2 degrees, this is relative to the pre-industrial conditions, will be exceeded during the 21st century unless deep reductions in carbon dioxide and other greenhouse gas emissions occur in the coming decades. So in fact, in the next 20 years, there's a very high chance that we will cross the 1.5 degree warming, next 20 years. So when we look at the, just a minute, yeah. So these are some of the, in the form of a table, The SSP 119 is one scenario where probably we will be the, even in this case, we will exceed the 1.5 degree in the next 20 years, even in the low emission scenarios. And in the midterm, the range could be, the best estimate is around 1.6 degrees, but the likely range could be anywhere, very likely could be somewhere between 1.2 to 2 degrees. And in the long term, we will be able to limit the warming by end of the 21st century below 2 degrees. This is the only scenario, that is the SSP 119, where it is possible to limit the warming to 2 degrees. That is as per the Paris Agreement. And when we go to the SSP 245, it's a kind of intermediate scenario. The 2 degree warming will be exceeded even in this case, very likely, because across from the different models, the range is anywhere between 2.1 to 3.5, and the best estimate is around 2.7. And in the next 20 years, we will cross the 1.5 degree warming. So so this is also going to, even the middle of the road is going to be a very challenging future. And one of the implications is that with every increment of the global warming in the future, the changes are going regionally, the changes in the mean temperature, precipitation and soil moisture are going to get larger. So this is the observed 1 degree warming. This is what we see in the observations, which is at present what we are seeing. And this is what is simulated by the model. When we have all the greenhouse gases and natural forcing, we are able to see this pattern of warming, more pronounced warming in the mid latitudes and the high latitudes, with lesser warming in the tropics and the low latitudes. And with 1.5 degree global warming, you can see this pattern is further exaggerated. You get more pronounced warming in the mid and high latitudes, in the polar latitudes, and even over the tropical areas. And the scenario is going to further amplify with at the 2 degree warming and 4 degree warming levels. And when we look at the corresponding changes in the precipitation, we see pronounced increase in the precipitation at the mid latitudes mostly, and also in the polar regions, and also over the monsoon regions of South Asia, West Africa and several areas in the tropics. But many areas in the subtropics, the Mediterranean, for example, will become dry. And also parts of Australia and South America. So all the subtropical areas, dryness will increase. So it is not that everywhere precipitation is going to increase. So the wet areas, the monsoon areas and the mid latitude and the high latitude areas, precipitation is going to increase with additional warming, and the dry areas are going to get drier. So it's like a wet gets wetter and dry gets drier kind of paradigm that we will be seeing. And what does that mean? So the dry areas where precipitation is going to projected to decrease with increased warming, there will be more increased evaporation, and the soil moisture will dry. There will be more drying, and because of the evaporative demand, so evaporation can decrease depending on the soil moisture. The evaporative demand will increase, and this can lead to more reductions in the soil moisture change. So this is one of the concerns. So droughts in these areas can become very severe, and the severity and frequency of droughts will increase in these areas. And what does it mean for extremes? So one of the consequences of temperature increase is the increase in the water vapor. So there is a Clausius-Clapeyron law which says that with every 1 degree warming, the water vapor in the atmosphere increases something like 7%. So if the water vapor is going to increase due to warming, the immediate consequence is that the heavy precipitation amounts will increase. And this is both in terms of the frequency and the severity. So what it means is now at present what is happening in the pre-industrial scenario, that is 1850 to 1900, what was happening once in every 10 years of a heavy precipitation is presently it's happening at 1.3. This is globally, and in the future with 1.5 degree warming, this will become 1.5 times more likely, and with 2 degrees this will be 1.7 times, and 4 degree it will become more frequent. And also the intensity of this precipitation, so it will increase. Likewise, with the heat extremes are also going to increase with further warming. So both the temperature and precipitation increase are projected to increase. They are going to get larger in frequency and intensity with every additional increment of global warming. And now with regard to the water cycle changes, in which I was one of the coordinating lead authors, we had three lead CLAs, one Herbie Duell and James Renwick from New Zealand. And we had about 13 lead authors from different countries and about 47 contributing authors. So they have also contributed. So different parts of this chapter, different people contributing authors have contributed, and there were 2 chapter scientists and one my own colleague, Dr. Sabin from IITM. And so this is a process-based chapter, as I said. And so this here we have an assessment of the global water stores. Basically, when we look at the total water available, much of it is there in the oceans, nearly 96.58% in the ocean, seas and bays. The saline groundwater and saline lakes, which they contribute about 1.61%, and the surface freshwater is about just 1.8%. Out of the surface freshwater, the usable part, which is basically in the form of fresh groundwater, permafrost, fresh lake, soil moisture, wetlands, atmosphere, artificial reservoirs, seasonal snow, rivers, and biological water. This is a very, very small contribution. This is what is really usable out of the available surface freshwater. The unusable part, which is shown in the green, it basically resides in the ice, and it is not really accessible to human. So freshwater is really, the usable freshwater is a very extremely rare commodity. And so with climate change, this is going to be a challenging issue. And now we also assess the water vapor fluxes, water fluxes from the different components of the Earth system. So the ocean evaporation being the dominant contribution of the fluxes, and much of it, what is evaporated from the ocean, is also goes into precipitation over the oceans, and it's also transported to the land, and this also contributes to the land precipitation. There's also evaporation from the land, from the cryosphere, and there is also assessment of the how much is used for the out of the precipitation, how much goes for the groundwater recharge, and what is the fresh groundwater discharge into the ocean. So various components of this water cycle components are assessed in the water cycle chapter. And I will now focus briefly on these monsoons, and especially this is the schematic of the South Asian monsoon, also known as the Indian monsoon. We have during the pre-monsoon months, starting from April, May, the land starts getting warmed. We have the massive Tibetan plateau, the Indian landmass gets heated up compared to the oceans to the south, and this sets up a kind of a pressure gradient, and this pressure gradient is an important trigger. So this thermal contrast and the pressure gradients lead to the setting up of the monsoon circulation, and due to the rotational effects of the earth, we have this monsoon cross-equatorial flow, a very large scale establishment of the monsoon circulation. But once the circulation, the monsoon flow is established, it also picks up a lot of water vapor, which evaporates from the Arabian Sea and from the Indian Ocean, and also from the Bay of Bengal. And this water vapor, this moisture-laden winds, when they interact with Western Ghats and the orographic of the Myanmar and other areas, they undergo forced uplift. They produce clouds as the warm air rises. It expands, and as the water vapor condenses, it forms clouds. And due to the condensation, we produce a huge amount of latent heat of condensation is released, and this in turn can maintain the circulation itself. And now with the satellite data, we are able to estimate how much is the latent heating that happens due to the monsoon precipitation. And of course, there are year-to-year variations in the seasonal rainfall. So typically the season goes from June to September. But this is also influenced by internal dynamics within the systems. We have active break cycles. We have synoptic systems like Bay of Bengal, depressions, lows and depressions. We have extreme precipitation events happening. So there's a very strong internal dynamics within the monsoon region, and also external drivers like the El Nino Southern Oscillation and also anthropogenic drivers. They can also influence the monsoon variability. So this is a very short summary of the introduction to the monsoon. So in the AR6, we have assessed both the global monsoon and the regional monsoons. In the AR5, in the fifth assessment, the assessment mainly focused on the global monsoon, which is shown by this black line, which is defined as global monsoon is defined as the area where the local summer minus winter precipitation rate exceeds 2.5 millimeter per day. And this was the definition used in the AR5. And the regional monsoons in the AR6, in the sixth, are defined based on published literature and the expert judgment, and also accounting for the fact that the climatological seasonal monsoon rainy season varies across the individual regions. So this assessment of the regional monsoons basically came from the water cycle chapter, and we have 6 regional monsoons. We have a South and Southeast Asian monsoon. This is shown by this pink color. We have the East Asian monsoon shown by the purple color, and we have the West African monsoon shown by the green area. These are only focused on the land precipitation, and we also have the North American monsoon and the South American monsoon, also the maritime Australia and the maritime continent monsoons. So these were the different regional monsoons that have assessed. In the AR5, the South Africa and also the Equatorial America were considered as regional monsoons based on the global monsoon definition. But in the AR6, we don't call them as monsoons because of course there is a strong seasonality in the precipitation. But calling them as monsoons is still it is a topic of debate. So in the AR5, we don't call them as monsoon areas, but we have assessed the seasonal changes in the precipitation in these 2 regions as well, which is shown by the dotted area. So the main assessment that comes out is that the global land monsoon precipitation has decreased from the 1950s to the 80s, partly due to anthropogenic aerosols, which I mentioned earlier, and but has increased since then in response to greenhouse gas forcing and also large-scale multi-decadal variability. This is a kind of medium confidence statement. And during the 21st century, global land monsoon precipitation is projected to increase in response to GHG warming in all time horizons and scenarios. This is a high confidence statement. And in the long term, global monsoon rainfall change will feature a robust north-south asymmetry characterized by greater increase in the northern hemisphere than in the southern hemisphere, and an east-west asymmetry characterized by enhanced Asian African monsoons and a weakened North American monsoon. So basically in the future, we are projecting that the Asian and the African monsoons are projected to increase, especially due to the increased GHG warming and also reductions in the aerosols. Anthropogenic aerosols, that's what is projected from by the models. And in fact, this is from the CB5 models. There is a kind of attribution of the different drivers. We have the greenhouse gases on the one hand, which is trying to warm the planet and also increase the precipitation. And then we have the aerosols, which are trying to cool, kind of offset the greenhouse gas warming effect. But the aerosol influence is mainly in the northern hemisphere, mostly in the land areas. So emissions from North America, Europe, and also Asia. And what we find is, so the temperature fingerprint of the greenhouse gas, we see a pronounced warming signature, most pronounced in the polar and the high latitudes. The temperature fingerprint of the aerosols is kind of cooling over the north in the northern hemisphere. But there's a kind of asymmetry, interhemispheric asymmetry. We have a cooling signature in the northern hemisphere and a kind of a warming signature in the southern hemisphere. And when we see the precipitation and fingerprints of the greenhouse gas and aerosol forcing, We see many areas in the mid-latitude and high-latitude increase in the precipitation due to the greenhouse gases. Subtropical areas kind of drying because of the subsidence, increased subsidence, some increase in the monsoon precipitation. But the aerosol fingerprint shows a decrease in the precipitation over many tropical areas. So we also now understand the reason why it happens. So if we cool one of the hemispheres relative to the other, due to the energy constraints, what we expect is that the ITCZ will shift. ITCZ is the intertropical convergence zone. It tends to shift to the hemisphere where it warms, so warming hemisphere. So this leads to this can lead to a decrease of the precipitation, and we do see the signatures of the precipitation and temperature changes even in terms of the aridity fingerprints. So the main point is there are different drivers when we talk about precipitation change and especially the monsoons. And in fact, in the northern hemisphere, we have as I said, the aerosols are basically reducing the shortwave radiation at the surface, incoming solar radiation. And now we have these observations in the northern hemisphere, what are known as the GBA, Global Energy Budget observations. What they show is that this black line shows from the 60s, there was due to the increased anthropogenic aerosol emissions, particularly from Europe and North America, and so there was a pronounced decrease in the shortwave radiation reaching the surface. This is known as dimming. So the dimming dominated the 1970s, 80s up to the 90s. And later on, due to the various regulations in the emissions, the aerosol emissions, the quality of the air quality has improved, especially in North America and Europe. And in addition, due to the continuation of the global warming and reduction in the aerosol forcing, especially over these areas, the monsoon precipitation slightly recovered, the global land monsoon precipitation. And this is what is seen. These are the radiation changes from the observations, and this is from the CMIP6 models. And one of the consequences of reducing the radiation is that the precipitation declined steadily. This is northern hemispheric land monsoon region. The precipitation declined. This is from the observations, the GPCC and CRU. And the models are basically able to roughly capture, although the magnitude of change is underestimated. And if you had only greenhouse gas, the precipitation is projected to increase, what is shown by this brown line. And so the aerosols are basically trying to reduce the precipitation in both the global monsoon region, whereas the greenhouse gases are trying to increase. So there's a kind of tug of war between these two different drivers. And there's also decadal variability. And we assess the changes in the monsoon precipitation from observations. This is for the period 1951 to 2014 for the South and Southeast Asia and East Asia in 2 panels. We have shown the trends from 3 different data sets, the Aphrodite, the CRU and GPCC, which is shown by these cross marks. And you can see a decrease in the precipitation over the South Asian monsoon region. And these are the CMIP6 models. This blue line is the experiment. If you had only natural forcings like the irradiance changes, volcanoes, and so on. So there you are not able to explain this decreasing trend because of the large spread across the models. In the all forcing experiment, which has the greenhouse gases, the aerosols, land use change. So the multi-model ensemble shows a decreasing trend. And the aerosol experiment, if you had only aerosol forcing, a clear decrease in the South Asian monsoon precipitation. If we had only greenhouse gases, we would see a contrast, we would see an increase in the precipitation. And of course, there are interdecadal and decadal variations, which are shown here, and the models kind of underestimate the decadal variability. But overall, the contrasting influence of the GHG and the anthropogenic forcing on the monsoon precipitation changes over South Asia and East Asia are captured clearly in the multiple models, CMIP6 models. And in the future, what we find is with reductions in the aerosol emissions and with continuation of global warming, because greenhouse gases have a long lifetime, they are going to stay there in the atmosphere for several decades, several centuries in fact, and the precipitation with continued warming, precipitation is projected to increase. So we have showing the near term is shown 2021 to 2040, mid-term is 2041 to 2060, and the long term is 2081 to 2100. We are showing three different scenarios: the SSP 126, that is the blue, yellow is the 245, that is the middle of the road pathway, SSP 585 is the high emission scenarios. So we see, especially in the middle and the long term, a very clear increase in precipitation over the South Asian monsoon region and also in the East Asian monsoon region. For the south, in the near term, there is a kind of if you see the spread across the model is larger. That is mainly coming because of the internal variability, which is supposed to dominate in the near term. So that is one of the sources of uncertainty in the near term. And what about the West African monsoon precipitation? As I said, due to the regulation norms in the aerosol emissions over North America and Europe, there was a precipitation reduction in the West Africa. They had long droughts in the Sahel region, especially in the 70s and 80s, and some recovery started after the 90s. There was a recovery in the precipitation, and this we are able to attribute it to the reductions in the aerosol to some extent, and also increased greenhouse warming, plus this decadal time scale, interdecadal variability of the system. And the West Africa also in the mid and long term, precipitation is projected to increase. So this is a quick summary. With regard to the current state of the climate system, we are able to, this is from the summary for policy makers. Human influence climate change is already affecting many weather and climate extremes in every region across the globe. Evidence of observed changes in extremes such as heat waves, heavy precipitation, droughts and tropical cyclones, and in particular their attribution to human influence has strengthened since AR5. And with regard to the water cycle, decreases in global land monsoon precipitation from the 50s and 80s are partly attributed to human caused northern hemisphere aerosol emissions, but increases since then, that is after since the 90s, have resulted from rising GHG concentration and decadal to multi-decadal internal variability. This is a medium confidence statement. Over South Asia, East Asia and West Africa, increases in monsoon precipitation due to warming from greenhouse gas emissions were counteracted by decreases in monsoon precipitation due to the cooling from human-caused aerosol emissions over the 20th century. This is a high confidence statement. And increases in the West African monsoon precipitation since the 80s are partly due to the growing influence of greenhouse gases and reduction in the cooling effect of human-caused aerosol emissions over Europe and North America. Medium confidence. And regarding the future, possible climate futures, continued global warming is projected to further intensify the global water cycle, including its variability. It's not only this means water cycle will increase, also the variability will increase. That's an important point. What it means is that the global monsoon precipitation will increase, but also the severity of wet and dry events will also increase. So there is strengthened evidence since AR5 that global water cycle will continue to intensify as global temperatures rise. High confidence, with precipitation and surface water flows projected to become more variable over land areas within seasons. High confidence, and from year to year, medium confidence. And precipitation is projected to increase over the high latitudes, equatorial Pacific and most parts of monsoon regions, but decreases over parts of the subtropics and limited areas in the tropics in SSP 245, 370 and 585, very likely. And a warmer climate will intensify wet and dry, very wet and very dry weather and climate events and seasons, with implications for flooding or drought. High confidence, but the location and frequency of these events depend on projected changes in regional atmospheric circulation, including monsoons and mid-latitude storm tracks. Monsoon precipitation is projected to increase in the middle to long term at global scale, particularly over South and Southeast Asia, East Asia and West Africa, apart from the far West Sahel. So medium confidence. And And also we have quickly, I will go through, we also made some assessments of the freshwater reservoirs. As I mentioned, I thought this may be of interest to the NGRI and the earth science community, where we have assessed the glaciers, the seasonal snow cover, the wetlands and lakes, very brief assessments. This mainly came from the contributing authors, and the groundwater. And as this is a famous picture from Rodel et al., which is also, we have adapted this in chapter 8 of the trends in the terrestrial water storage based on the GRAY satellite data. Observations from April 2002 to March 2016, where we can see precipitation trends in the groundwater, which can come because of extraction, human extraction. So mostly human impact, groundwater extraction, and there are areas which have also experienced droughts, which has also affected some areas the groundwater, and also because of changes in the precipitation, and also the climate change impact. So this picture has been adapted from the Rodel et al. And the main assessment of the groundwater, the observed changes is that, in summary, there is medium confidence that increased precipitation intensities, partly due to human influence, have enhanced groundwater recharge, most notably in the tropics. This is some parts of Africa. We had one contributing author, Richard Taylor. He contributed to this assessment, and there is high confidence that groundwater depletion has occurred since at least the start of the 21st century as consequences of groundwater withdrawals for irrigation in some of the world's most productive agricultural areas in drylands, such as the southern high plains and California Central Valley in the USA, the North China Plain and Northwest India. For the future, this is in summary, based on known limitations in current modeling, no confident assessment of groundwater projections is made here, although important climate-related changes in groundwater recharge are expected. In many environments, such climate-related impacts are expected to occur in the context of substantial human groundwater withdrawal, depleting the groundwater storage. And with regard to the glaciers, in summary, human-induced global warming has been the primary driver of global glacier recession since the early 20th century. This is a high confidence statement. Most glaciers have lost mass rapidly since the 1960s and in an unprecedented way over the last decade. So thereby contributing to increased glacier runoff, especially from larger glaciers, until a maximum is reached, which tends to occur later in basins with larger glaciers and higher ice cover fractions, high confidence. In summary, this is for the future. In summary, glaciers are projected to continue to lose mass under all emission scenarios, very high confidence. Runoff from glaciers is projected to peak at different times in different places, with maximum rates of glacier mass loss in low latitude regions taking place in the next few decades in all the scenarios, high confidence. While runoff from small glaciers will typically decrease because of glacier mass depletion, runoff from larger glaciers will increase with increasing global warming until glacier mass is similarly depleted, after which runoff peaks and then declines, and which tends to occur later in basins with larger glaciers and higher ice cover fractions, high confidence. Glaciers in the Arctic and Antarctic will continue to lose mass through the later half of this century and beyond, high confidence. So with regard to the seasonal snow cover, in summary, if a decline in this springtime northern hemisphere snow cover extent, snow depth and duration has been observed since the late 1960s and has been attributed to human influence, high confidence. Depending on the region and season, there is low to medium confidence in the main drivers of snow cover changes, although various regions exhibit a shortening of the snow cover season, which is consistent with global warming. And of course, there's a more detailed assessment of seasonal snow cover chapters in chapter 9, which is focusing on the oceans and cryosphere. In summary, this is for the future projections of the snow cover. In summary, based on the results of chapter 9, it is now virtually certain that now future northern hemisphere snow cover extent and duration will continue to decrease with global warming. While most studies have focused on northern hemisphere, in the northern hemisphere, process understanding suggests with high confidence that these results apply to the southern hemisphere as well. There is high confidence in snowmelt occurring earlier in the year. Changes to the timing and amount of snowmelt will have strong influence on all the other aspects of water cycle in regions with seasonal snow, including runoff, soil moisture and evapotranspiration. And also there is an assessment of wetland and lakes, which is also an important freshwater reservoir. In summary, there is this is for the observed change. There is high confidence that the extent of human-made surface water has increased over the 20th and 21st century. These are mainly reservoirs and others, which has increased the human-made surface water. In contrast, due to limited agreement in the observational records at the global scale, there is only low confidence in the observed decline of natural surface water extent in recent years. So this is also in the special report on land and for the future with regard to the wetlands and lakes. In summary, there is medium confidence that inland wetland extent will decrease in regions of projected precipitation decrease and evaporation increase. And high confidence, this is typically like the Mediterranean areas, and high confidence that sea level rise will increase saltwater intrusion into coastal wetlands. However, there is low agreement on the influence of sea level rise on the extent of coastal wetlands. Regarding lakes, there is high confidence for temperature increases and ice decreases based on both projections and physical explanations, and low confidence for non-homogeneous decreases in mixing, given there is currently limited evidence. Yeah, so these were the points I thought I should present, and thank you very much for your kind attention. I am happy to take questions. Thanks a lot.
Thank you very much, Dr.
Yeah.
There are a few questions.
Yeah, can I stop sharing the screen?
Yeah, sure.
Yeah.
So there's a question from one of senior retired colleagues, Dr. Shakil Ahmed, and he would like to know whether there's any study on the balancing of the ice/snow melting, that is increase of water and high evaporation, that is decrease of water at any given space and time, because both are caused due to rise in temperature. So the counter effects, is there any study that explains the balancing of these two?
Balancing of what too? Can you please repeat it?
Balancing of snow ice melting versus increase of water due to high evaporation. So you have countering effects.
Because definitely it is going to increase the runoff due to the increased melting. But I don't know, normally the increased runoff is much more than the increase in this is what I would expect, increased evaporation in these areas. Maybe I have to get I have to look into the assessment. Probably this basically came from one of the experts who worked on the ice, and so I can probably get the feedback from him. And yeah, whether there are published literature, we have to see.
Okay, yeah, thank you. Any other question from colleagues from NDRF? You may please raise your hand if you have any question. Dr. Vineet Gehlot, yes.
Hi, Dr. Krishnan.
Hello, Dr. Vineet. Yeah, nice to see you.
Thanks.
Very nice to have a nice background with a lot of glaciers.
Yeah, there are few glaciers in the background, you see. I mean, please excuse me for my ignorance if the question sounds stupid.
No problem.
But I was only trying to look at the impact in Antarctica, and what I found was that impact from the observations, the impact on Antarctica is probably minimum, But then when I look at the simulations which you showed in subsequent slides, the impact seems to be higher in an Arctic and Antarctic region. So is there a kind of these are two contrasting things which are happening, that observations say that the impact is low, but the simulation says that the impact is going to be high on Arctic and Antarctic region. Is it? Am I correct? I mean,
yeah, you are correct in a way. You are right in a way. In the Arctic, for example, Arctic, I think there is a increase in the temperature. Warming, we call it as the Arctic amplification, and there is also increased ice melt. And the projection is that Arctic will be ice free in the next few decades. I mean, in the next few decades. And so the models are basically responding to the increase of the carbon dioxide, very pronounced. And also it depends on the sensitivity of the models. There are people, they do what is known as the equilibrium sensitivity experiment. So it varies, the equilibrium sensitivity of models, it varies from models. There are some models which have very high sensitivity. So if you increase double the carbon dioxide, how much is the surface temperature increase? So that can be very large in some models, and some are kind of moderate sensitivity and some are low sensitivity. So the IATM sensitivity is kind of a moderate kind of sensitivity. There are some models for the UK Met Office or the Norwegian models. They show very amplified warming. So that depends on the feedback processes, because when the ice starts melting, the albedo also decreases. So once there's a decrease in the albedo, you tend to absorb more heat, and that is further going to amplify the warming. So that's a kind of positive feedback. So these feedbacks can vary from model to model, and that can affect the equilibrium sensitivity. But the point is, in the Arctic, at least they are all showing increased warming very consistent with observations. The models, all of them are showing. So across there is a spread, as you rightly said, there is a spread across the models, widespread across the models. But the sign is correct, mostly correct. In the Antarctic is a slightly tricky business, because there is a lot of natural decadal variability within the system. Since 2016, I know that there has been a decrease in this sea ice in the Antarctic, especially started in 2016, and we are also seeing the increases in temperatures in some parts. So, but Antarctic region, the decadal variability the natural variability is much stronger, and I think the models are not able to respond to that. So models, they are basically responding to this external forcing, the anthropogenic forcing by the greenhouse gases very strongly, and they show that they see that the temperature is increasing in the Antarctic, and so accordingly they are projecting declines, but they are not able to capture some of these decadal timescale, decadal variabilities. So that may be a kind of conflict. And also the Antarctic ice sheet, it is something known as a deep uncertainty. I didn't mention. So we know very little about the ice sheet processes, particularly in the Antarctic, and that is a deep uncertainty. Normally that word is not used. So even in the IPCC, deep uncertainty word is a highly restricted word. They don't use it because our knowledge is very limited. It's highly uncertain. So Antarctic, still many things we don't know. So you're right in that way. We need to do a lot of research.
Thanks.
Yeah, thank you so much.
Dr. Krishnan, I have one just query.
Yeah.
We do see the impact at the regional as well as the global level of El Nino. But what I see in the model as well as in the observation, there is a drastic change before around 90, or probably it might be coinciding with 87, 88 big El Nino event. So is there very specific about that which has made a big difference at the global level as well as the regional level?
Yeah, so the thing is, after 97 there was this big El Nino, and 90, and people are thought that we should get a big decrease in the monsoon, and it was a kind of near normal monsoon. And at that time, say around 1999, this IOD also, Indian Ocean Dipole also came. And 1997 was one important event. Although there was a big El Nino, there was this influence of this IOD, which kind of favored the monsoon. That we are, at hindsight, we are able to see that. And with regard to the models, now, so you're talking about the weakening relationship, and then Krishna Kumar and other people, they wrote a science paper telling that the ENSO and monsoon relationship has weakened in the recent periods, maybe because of global warming. That was the first part. And subsequently in 2006, they wrote another science paper where they argued that if you have warming in the Central Pacific, its influence on the monsoon precipitation is more pronounced than the warming in the Eastern Pacific. So the 1997 event was more of a warming in the Eastern Pacific. So basically they were talking of different flavors of El Ninos. What kind of weather is the Eastern Pacific warming or Central Pacific warming? So the Central Pacific, and now Ashok Karumuri, who is now on Hyderabad, he is also talking about this Modoki, which is more of a Central Pacific warming that has a more stronger impact. So, and now whether the relationship has weakened. Now there was another paper which talked about this linkage between El Nino and monsoon on how on decadal time scale it can vary. And I mean, this is from the German group, and they do what is known as a phase coherence analysis. They are telling you these are oscillatory systems. The El Nino Southern Oscillation is an oscillatory system of the climate. Likewise, the monsoon is also an oscillatory system. And if you want to look at the relationship, it is just, you cannot look at only just the variation, the strength of the signal. You have to also look at the phase of the oscillation. What happens? So they use some nonlinear technique, and we also did that. And they find that there are certain epochs where the El Nino and there's a phase synchronization of the El Nino and the monsoon, and there are some epochs the synchronization is less. And people are trying to understand. One of the reasons they projected that whenever there is a major volcanic eruption, like the Pinatubo or the Krakatoa, these type of eruptions can, if there's an external forcing, then these two oscillatory system can lead to a phase synchronization. And we also saw that in our recent paper, which we published in Science Advances. So these oscillatory systems can be affected by large volcanic eruptions due to changes in the radiation and so on. So this is an ongoing research, and models do show the signatures of the ENSO on the precipitation. In fact, they overdo it. And what is really important, I think, for the seasonal prediction is looking at the Indian Ocean variability, the IOD particularly. What is its impact on the monsoon? I think that's where we are having shortcomings. The ENSO signature on the monsoon is, in fact, it is overemphasizing that. The models try to overemphasize, at least our IATM model, monsoon vision model. Yeah, so the advance, definitely that there has been an improved understanding of the ENSO and monsoon connections. But also how climate change will affect ENSO. People have studied that. Generally, they say that with global warming, you should get more like a El Nino-like pattern in the SST. This is what is projected. And of course, there are different views. The group in Lamont doesn't agree with that. They have a different view. So these are still ongoing topics. How the internal variability will be affected, how the coupled system will vary and things. Yeah.
Thank you. I have another question, which was not very very specific in your talk, but I know that you have an interest of the northwest Himalayan glaciers, particularly Pamir and Karakoram. And we do know that they are waxing for last at least 1 decade or so, or more than a decade or so, while the temperature is increasing. There are some kind of explanation based on the westerlies given, but do they have also interconnectivity with the global events, or they are still localized, dominated by westerlies?
Yeah, Yeah, it's a very good question. Actually, this we have also assessed this. Maybe I didn't mention in my talk. So these, especially these Pamir regions and the Karakoram regions of the Himalayas, where there has been a slight increase in the snow and glacier, slight, and so there's a positive mass balance, which is unexpected, and the people are calling it as the Karakoram anomaly. So this is assessed in the chapter. I think there's a small cross-chapter box. And all the related references. And what we also found was with the global warming, in a global warming scenario, because with more increased warming, especially over the Tibetan plateau in the east, so it can alter the large scale and alter the large scale pattern circulation, especially in winter time, which is favorable for very strong western disturbances to amplify. And that can produce substantial wintertime precipitation over the Karakoram region. So that may be protecting, and a similar group paper came from GFDL also. So wintertime precipitation may be protecting that region. So it looks like it is it's a very, not a very common feature. This is a kind of very unique feature for this region. Interaction of the westerlies with the Karakoram region and producing this precipitation. Yeah, so some of the models are able to show that, and this is in fact assessed in the IPCC also.
Thank you.
Yeah.
Thank you very much.
Thank you, sir. I think there is one more question there. Somebody has raised.
Yeah, Akash, please go ahead. Looks like you're muted.
Akash Asoka. नीचे हैंड जाके देखिए.
हाँ ये.
Am I audible, sir?
Yeah.
Yes, sir. Okay. Thank you, sir, for the wonderful talk. Actually, I have one doubt. Like under warming scenario, how the cyclonic activity over Indian region will change, especially in the nowadays in the western part of India, the activity is increasing, and how it will change in the future. Your insight on that.
Yeah. Thank you very much, Akash. Yeah, that's a very good question. So one of the things is with the increased warming, the oceans are absorbing energy, as I showed earlier. Indian Ocean has been warming, so the Arabian Sea has been warming. Heat content has increased. So that is one of the conditions, prerequisite. Warm SSTs are one of the prerequisites for tropical cyclones. But there are other factors like the vertical shear of the wind, and you also require more mid-level humidity. And so there are a number of other factors which is also going to determine the cyclone formation. And so now, as you rightly said, we are seeing just in the Indian Ocean, for example, normally we get the cyclones during April, May, June, for example, before the monsoon season, and maybe in the post-monsoon season. And but during the monsoon season, because we have a very strong vertical wind shear, the cyclone formation is suppressed because of the vertical shear of the monsoon circulation itself. And the assessment is that some of the this came from our national assessment report, the very severe cyclonic storms, they have become more severe, especially in the Bay of Bengal post-monsoon. And now we are seeing the Arabian Sea cyclones also, especially during the pre and post monsoons. And so that is so definitely they are going to intensify. They can intensify, there's a high chance, but only thing is the numbers to make in terms of changes in the frequency, it's going to be challenging how to weather because we don't have long enough data to say that. And one thing, probably their intensity is going to increase, that we can probably project. but on the frequency of the storms is more challenging. In fact, globally also they have not found a increase in the frequency of storm with global warming. The very high categories, category 4, category 5 type of cyclones, they can get stronger. There is a confidence, but in terms of the frequency, still it is a kind of low confidence or medium confidence statement.
Yes, sir.
Yeah.
Thank you very much, Dr. Krishnan.
Yeah. Thank you, Doctor.
End of this program, but once again, I would like to wish happy Earth Day to all of you, all of my colleagues. It's now my pleasant duty to propose a formal vote of thanks, and I must mention that I'm doubly elated, not only because the speaker is a highly renowned climate expert in the country, globally known, but also because he's a very good friend of mine, and I had the privilege of working with him and having long discussions during meetings with him when I was in MOS. So thank you very much, Dr. Krishna. That was a very exciting talk. And in fact, you covered such an important topic, in fact, a topic of tremendous importance, that is the impact of global climate change on the hydrological cycle. There cannot be a more important topic at the moment. So, and I'm also thankful to you for sharing with us through a very comprehensive description of the IPCC report. And I must congratulate you for being the lead author in this very important report. But I also should mention that you started on a very alarming note when you said that there is unprecedented impact of the anthropogenic factors in the last 2000 years. So I'm sure that's an alarming piece of news for a lot of us. Then you took us through a very interesting journey where you covered the ocean level rise budgets and contributes, the socio-economic challenges and the future projections for global warming. And you also highlighted the importance of the water cycle changes that are likely to take place in the future, and the effects on the South Asian monsoon, changes in the climate futures. And that was very interesting, where you showed us what we can expect regard to glaciers and their recession, one of the most alarming issues that we are facing, the availability of fresh water and snow cover changes and so on. And this is really alarming because we as geoscientists, we also address of geohazards, particularly in the Himalayas. So the recession of glaciers and the gulfs that would follow is certainly a very, very big challenge for all of us.
That's true.
In fact, I would like to mention that NGRI has also started working on monitoring of glaciers using seismic networks.
Very nice.
Our work it came in Science last year, you may be aware of that. So your talk certainly has a huge implication for NGRI and the studies that are going on here. So with these few words, I would like to once again thank you for a very exciting talk, and I'm sure there will be a lot more questions that we can go through days to come. Yes.
Thank you, Dr. Purnachandra.
Thank you for accepting our invitation. I think it was very apt for the Earth Day that you very readily agreed to be with us. So thank you very much.
Yeah, my pleasure, Dr.
And I also like to thank all our colleagues
for all the kind words, and I really enjoyed this talking to all of you.
Yeah, I think the interaction was also very good and
very
good discussions. So I would
Thanks
also
a
like
lot
to
for giving me this opportunity.
I would also like to thank all colleagues from CSR, NGRI, and many of our retired colleagues who took time out to come and attend this wonderful talk. And I must also thank our colleagues from the information section and from the IT section who made the arrangements for this talk. So thank you very much. And of course, I'm very grateful to the director who has been 100% with us. He always is for any such programs that we need to organize. Yes. And of course, Dr. Devendra Kumar, who has taken the responsibility to organize the whole thing. Thank you once again to all of you, and particularly
Thank you, Dr. Virendra Tiwari ji and Dr. Devendra Kumar. Thank you, Dr. Purnachandra.